Welcome to the first video in our series, AI Teaching GenAI System Design. In this series, we'll explore how to systematically design generative AI systems, from understanding core model types to building robust, scalable, real-world solutions. Before diving into system design, it's important to understand the foundation: machine learning models. Broadly, these can be split into two categories. Discriminative models, which are like skilled judges. They focus on distinguishing between classes, predicting outcomes, and making decisions based on input data. Examples include logistic regression, SVMs, decision trees, KNN, and neural networks. Generative models, on the other hand, are more like creative artists. They learn the underlying patterns of the data and can generate entirely new examples. Examples include Variational Autoencoders, VAEs, GANs, diffusion models, and autoregressive models like GPT. Understanding these distinctions is key because generative AI relies heavily on modeling and replicating complex data distributions, which directly impacts how we design, train, and deploy these systems. In this first video, we'll also cover what powers generative AI, data, model capacity, and compute. A structured framework for Gen AI system design, from requirement clarification to deployment and monitoring. The essential steps in designing a generative AI system, including data preparation, model development, evaluation, and overall system architecture. By the end of this video, you'll have a clear roadmap for approaching Gen AI system design, whether it's for an interview, a project, or a production system. Let's get started by understanding the different types of machine learning models and how they form the foundation of every generative AI system. Let's start by splitting machine learning models into two broad categories: discriminative and generative. 1. Discriminative models. These models focus on learning the boundary between classes. They don't try to understand the entire data distribution. Instead, they concentrate on telling one class apart from another. Logistic regression, a classic linear model that estimates probabilities of class membership using the logistic function. Great for simple, linearly separable problems. Support vector machines, SVM, finds the optimal decision boundary, or maximum margin, between classes, particularly effective in high-dimensional spaces. Decision trees, splits data based on feature values into decision rules. Very interpretable, but prone to overfitting without pruning. K-nearest neighbors, KNN, classifies a point based on the majority vote of its nearest neighbors in feature space. Simple but computationally expensive for large datasets. Neural networks, layers of interconnected nodes that can capture complex, nonlinear relationships, can be scaled from small models to deep learning architectures. Key idea: discriminative models answer the question, given this data point, which class does it belong to? Second, generative models. These models learn the underlying data distribution, meaning they try to capture how the data was generated. Once trained, they can create new, realistic examples. Variational Autoencoders, VAEs, encode data into a latent space and decode it back with a probabilistic twist that allows sampling of new data points. Generative adversarial networks, GANs. Two networks in a game. A generator creates fake data, and a discriminator tries to tell it apart from real data. This adversarial process produces incredibly realistic outputs. Diffusion models. Gradually add noise to data and learn to reverse this process, producing highly detailed, high-fidelity images. Autoregressive models generate data one step at a time, where each step is conditioned on the previous outputs, e.g., GPT for text generation. Key idea: generative models answer the question, can I model the world so well that I can create new, convincing examples? Think of discriminative models as skilled judges. They're great at deciding which class something belongs to. Generative models are more like artists. They learn the essence of the data and can create new works from it. Let's talk about what truly powers today's generative AI. It comes down to 3 pillars: data, model capacity, and compute. First, data generative AI thrives on self-supervised learning. This means the model can learn patterns and relationships from vast amounts of unlabeled data. Think of predicting the next word in a sentence, the missing patch in an image, or the next note in a melody. The beauty here is scale. Since most data in the world is unlabeled, this unlocks orders of magnitude more training material compared to traditional supervised learning. 2. Model capacity. Model capacity refers to how much the model can actually learn and store. 2 key measures are number of parameters. These are like the memory cells of the network, and modern models can have hundreds of billions of them. More parameters often mean the ability to capture more nuanced relationships, though with diminishing returns. Flop count, the number of floating point operations needed for training or inference. This measures computational complexity and is tightly linked to both cost and capability. 3. Compute. This is the raw horsepower that makes it all possible. CPU, versatile, great for general tasks, but slower for massive parallelism. GPU, the workhorse of AI, with thousands of cores optimized for matrix math. TPU, custom chips from Google built specifically for AI workloads, especially efficient for large-scale training. Finally, there's the scaling law, an empirical observation that model performance tends to improve predictably with more data, larger models, and more compute. This is why the biggest breakthroughs often come from pushing all 3 dimensions together. In short, generative AI's power is a product of massive datasets, huge models, and immense compute, all working in harmony. When tackling a GenAI system design interview, it's crucial to approach the problem systematically. Clarifying requirements. Start by deeply understanding the problem domain. Ask clarifying questions about the goals, constraints, and success metrics. For example, if the interviewer says, "Build a content summarization tool," you should clarify, is it for text, audio, or video? What's the target length of the summary? How will the output be evaluated? Also probe for business context. Sometimes the why can shape the how. Framing the problem as an ML task, identify whether this is a supervised, unsupervised reinforcement, or generative learning problem. In GenAI contexts, framing also means deciding between fine-tuning an existing foundation model versus training from scratch, or even using retrieval augmented generation, RAG. Data preparation. Define what data you need, how you'll source it, and how you'll clean and pre-process it. In GenAI, this often includes prompt engineering data, synthetic data generation, and high-quality human annotations for fine-tuning. Model development. Decide the model architecture, transformer-based, encoder-decoder, or multimodal. Discuss trade-offs, parameter size versus latency, open source versus proprietary, and methods like LoRa or QLoRa for efficient fine-tuning. Evaluation. Go beyond accuracy. Consider BLEU, Rouge, perplexity, factual consistency, or human preference ratings. For GenAI include robustness tests, e.g., prompt sensitivity, bias analysis, and adversarial prompt handling. Overall ML system design. Show how the model fits into the end-to-end system. Input pipelines, feature stores, model serving, caching, and retrieval layers. Address scalability, fault tolerance, and cost efficiency. Deployment and monitoring outline deployment strategies, A/B testing, shadow deployment, or canary release. Emphasize monitoring for drift, hallucinations, latency, and user feedback loops. In production, GenAI systems, continual learning and safeguard layers, e.g., moderation models, are often essential. The goal is to walk the interviewer through your structured thinking while showing awareness of the unique challenges of GenAI, large model sizes, data sensitivity, and unpredictable behavior. The first step in designing any GenAI system is to clarify the requirements. This stage lays the foundation for everything that follows. We break this down into functional and non-functional requirements. Functional requirements focus on the core capabilities the system must provide. For example, if building a text generation system, clarify if it needs to handle multiple languages, styles, or specific content types. Understanding what the system should do guides the model and architecture choices. Non-functional requirements. This category captures the broader context and constraints around the system. Business objective. Understand the why. What is the system's ultimate goal? For instance, is it to boost engagement, automate tasks, or enhance user experience? This drives priorities and trade-offs. System features. Identify key features beyond core AI tasks, like user feedback integration, logging, access control, or interpretability. Data. Clarify what data is available for training and validation. Is it proprietary, public, or synthetic? What is the data quality and volume? Data often limits or empowers model design. Constraints. These could be technical, hardware latency, legal, privacy, compliance, or budgetary. Constraints strongly influence system design decisions. System scale. Assess expected user load and data throughput. A system for millions of daily users demands different infrastructure than a niche internal tool. Performance. Define measurable metrics like accuracy, latency, throughput, and uptime. These help set expectations and monitoring criteria. By thoroughly clarifying these requirements up front, you set yourself up for a focused, efficient, and aligned system design process. Always remember to ask clarifying questions during interviews to ensure full understanding. Once the requirements are clear, the next step is to frame the problem properly as a machine learning task. This involves carefully defining the system's inputs and outputs and selecting an appropriate modeling approach. 1. Specifying system's input and output. Clearly define what data the system will receive. For example, raw text, images, audio, or a combination. Then, specify the expected output. Is it a classification label, a generated sentence, a prediction, or a ranking? This input-output definition sets the stage for the entire modeling pipeline. 2. Choosing a suitable ML approach. Decide whether a discriminative or generative model better suits the problem. Discriminative models learn to distinguish between classes or predict outputs directly from input features. They are often used for classification or regression tasks. Generative models, on the other hand, learn the underlying data distribution and can generate new, realistic data points. These are ideal for creative tasks like text or image generation. 3. Identify the task type. Determine if the problem is supervised learning, with labeled data, unsupervised learning, finding structure without labels, or reinforcement learning, learning via feedback. In GenAI, many tasks are generative, but framing can also include retrieval, ranking, or hybrid approaches. By framing the problem clearly at this stage, you make sure your ML solution is aligned with the business goals and technical constraints, setting the foundation for successful model development and deployment. Data preparation is a crucial foundation for any generative AI system, as the model's quality and reliability heavily depend on the data it's trained on. First, data collection. Generative AI typically requires massive volumes of data, often unstructured. Think text from the web, images, videos, and audio. This data diversity enables the model to learn rich representations and generalize well. Collecting such data involves scraping, licensing, or aggregating from multiple sources, which must be done responsibly. Data cleaning raw. Unstructured data is noisy and inconsistent. It may contain duplicates, irrelevant content, errors, or harmful biases. Cleaning involves filtering out bad data, correcting errors, normalizing formats, and ensuring quality. Effective cleaning improves model performance and reduces risks of generating problematic outputs. Third, data efficiency, storage and retrieval. Handling huge datasets demands efficient storage solutions, scalable data lakes, or distributed file systems. Retrieval systems are also critical. The ability to quickly access relevant subsets during training or fine-tuning can save time and compute. Techniques like indexing, caching, and embedding-based retrieval help optimize these workflows. In summary, a thoughtful data preparation pipeline turns raw, messy data into a reliable, high-quality asset that fuels generative AI's capabilities. Investing effort here pays dividends downstream in model accuracy and robustness. When we move into the model development phase, we're taking the cleaned and prepared data and using it to build the core intelligence of our GenAI system. First, model architecture. We begin by selecting an architecture suited to the problem. For most cutting-edge GenAI applications, the transformer architecture dominates, thanks to its self-attention mechanism that allows models to capture long-range dependencies in text, images, and other sequential data. But it's not just transformers. Depending on the domain, we might still consider CNNs for vision tasks or hybrid models that combine multiple architectures. Second, model training here, we define our training methodology. This includes whether we're training from scratch, fine-tuning a pre-trained model, or using reinforcement learning, such as RLHF in conversational AI. We decide on the training data, which might be massive, heterogeneous datasets, and clarify the ML objective and loss function that will drive optimization. Third, task-specific challenges and mitigations training. GenAI models at scale is resource-intensive and technically complex. Techniques like gradient checkpointing help reduce memory usage. Mixed precision training speeds up computation while lowering resource requirements. Distributed training is a must for large models. Here we can use data parallelism to split batches, model parallelism, pipeline or tensor to split the architecture itself, or hybrid parallelism for maximum efficiency. Finally, model sampling once trained, we need to generate outputs. This is the sampling step. In text generation, for instance, we might use top K sampling, nucleus sampling, or temperature scaling to control diversity and creativity in outputs. In diffusion or GAN-based models, sampling involves iterative steps to create realistic new data. In short, this phase turns theoretical design into a functioning, optimized AI model, balancing architecture choice, training strategies, and sampling methods to meet the system's goals. In the evaluation phase of a generative AI system, we assess the model's quality and effectiveness both offline and online. Offline evaluation focuses on controlled, repeatable tests using benchmark datasets. For text generation, we look at metrics like perplexity, how well the model predicts the next word, BLEU and Meteor, alignment with human-written references, and Rouge, overlap in n-grams, often used for summarization. For image generation, metrics like FID, Fréchet inception distance, measure similarity to real images. IS, inception score, evaluates image diversity and quality. KID, kernel inception distance, handles small dataset bias. SWD, sliced Wasserstein distance, assesses texture, and PPL, perceptual path length, captures smoothness in latent space. For text to video, we use FVD, Fréchet video distance, FID and KID adapted for temporal content, CLIPSCORE, semantic alignment between text prompt and video, and LPIPS, perceptual similarity. Online evaluation happens in real-world scenarios, usually via A/B testing. Here, we measure business and user-centric KPIs, click-through rate, conversion rate, revenue per user, and user satisfaction. The goal is a balanced approach. Offline metrics help us iterate faster without user impact, while online metrics confirm real-world value and ensure the model benefits both users and business objectives. When we reach the overall system design phase for a GenAI system, we're looking beyond just the model to consider how the entire ecosystem works together in production. 1. System components. We start by identifying all key building blocks, from data ingestion pipelines, feature stores, and model-serving infrastructure, to APIs, UI layers, and monitoring dashboards. In a GenAI context, this might also include retrieval-augmented generation modules, content filters, and embedding databases. A well-architected component layout ensures each piece integrates smoothly while being maintainable and extensible. Second, user feedback and continuous learning. Generative AI thrives on iteration. Incorporating feedback loops, whether explicit user ratings, implicit behavioral signals, or content flagging, helps retrain or fine-tune models to keep them relevant. This is especially critical in domains like chat assistants, recommendation systems, or creative content tools, where user preferences evolve quickly. Third, scalability. GenAI workloads can be computationally expensive. We need to design for horizontal scaling, serving multiple requests in parallel, and handle traffic spikes gracefully. This includes model sharding, caching strategies, and elastic infrastructure, so performance remains consistent even under high demand. Fourth, bias prevention. Generative systems can unintentionally amplify societal biases present in training data. We mitigate this through careful dataset curation, prompt filtering, and fairness-aware training techniques. Regular audits of generated outputs are essential to ensure ethical and inclusive behavior. 5. Robustness and security. Finally, we must ensure the system is resilient to adversarial attacks, prompt injection attempts, or data poisoning. This also means robust error handling, model rollback plans, and privacy safeguards for user data. The overall design phase is about turning a good model into a safe, scalable, and user-aligned product. Without it, even the most advanced GenAI model risks failing in the real world.